It's not. It's a long title. You probably wouldn't see it in the blockbuster movie screen for the summer, but still interested enough, informative. So with that, we'll have at it. So the general outline is we'll look at the problem space. We'll give the crashiest of crash courses, I think, in gravitational waves. We'll go over methodology, things like what is a GAN, the general architecture of a GAN, and then what did that look like for my project specifically. Then we'll blow through some analysis of results for the sake of time. We're going to look at the output of the models, and then we're going to look at the training performance across all. So the problem space is investigating gravitational waves with generative AI. In this case, generative AI is going to be the GANs, a generative adversarial network. The end goal for the first part is to improve the ability to detect genuine gravitational waves by better understanding glitches. I'll get on to glitches in a minute. And then the secondary goal is to investigate different architectures for GANs. So there's a Gangly library that was created by Melissa Lopez. And I wanted to compare how her generator is set up compared to an idea that I had and see if there's any difference between the two. So the crash course, but gravitational waves, I think a couple people have talked about it at this point. High level overview, they're ripples in space-time caused by some very energetic and violent processes, things you really don't want to be anywhere near. And then they were predicted by Einstein in 1916 with the general theory of relativity. He thought that they wouldn't be able to be detected because they were too weak. However, they were first indirectly detected in the 1970s, and then they were directly detected in 2015 by LIGO, a US-based interferometer group. Here is on the right, you'll see an example of the first genuine detection. So it's a chart. You actually can hear it in audio. It'll go whoop. So it's pretty cool to hear on YouTube. And on the left is an example of an interferometer. You have two black holes about to coalesce, and the interferometer is going to pick up those gravitational waves. That's essentially the instrumentation that we're looking at on a large scale. Now, what are glitches? If these are real, glitches are a bit more confusing. It can be transient noise artifacts that can either come from phenomena in space, or it could happen on Earth. It could be something as simple as a truck driving relatively closely past the interferometer that can inject some noise into some signals, and it can complicate the whole detection process. For example, you can have a glitch sitting on top of a genuine gravitational wave, which would make it very difficult to suss out which is real and which is not. But by investigating glitches, you can better understand what the genuine signals are. So for the methodology, here's an example of the training data. Detecting gravitational waves does not look anything as clean as the stuff you see at the top. Some glitches you would see on the bottom. So these are genuine glitches that have been detected. For simplicity's sake and to not over-engineer a data pipeline, I used synthetic data, where I decided to plug in a couple of different functions and see what the models would output, with the assumption being that you can use the Gaussian pulse and kind of see some similarities in the QQ transforms on the bottom. So it's nothing you would put into production, more of an ideas-based thing. Now for model training, there's going to be 3 different iterations that I go through here. One model is using the already existing GAN in the Gangly library, created by Melissa Lopez. Then I'm going to use the Gaussian pulse data on that. Then I'm going to take Gaussian pulse data on my setup for a GAN. And then I'm going to take the sine waves and I'm going to use that on mine as well. With the idea being I can compare Gaussian pulses between my own and the current existing research, and then I can try to push mine a little bit further with the sine waves representing a slightly more complex function to represent. Overview of a GAN, you can see the plot up there. A helpful analogy is kind of banks and robbers, where if you wanted to counterfeit money and you lived in this alternate universe where you can infinitely go up to the bank teller and say, hey, does this look real to you? You show up with a blank piece of paper and they're like, that's definitely not a $100 bill. And you just burn through thousands and millions of iterations. And eventually you'll land on something due to the feedback of the teller telling you no so many times, you'll learn and you'll have a pretty good idea of what a $100 bill looks like. And then you'll be off to the races and probably in jail. This is what a deep convolutional GAN looks like. Same architecture as before that you would see. Gangly uses some clever tricks. They for loop over the discriminator because the discriminator is pretty much has the most important role in this whole process. And there's some penalty terms like gradient penalty and consistency term, which I won't get too much into, but those certainly help to stabilize the training process. And the deep convolutional generator, that's where I was taken around with myself. That's generally the idea of it. You take 100 random samples and you put that data into the generator, and it should give you something that looks similar to your training data. Now, here's the idea that I was chasing, the checkerboard artifacts. This exists in images that you can see in the top right. Basically, as filters are passing over each other, the overlap will create that pixelated checkerboard pattern, which has been seen frequently with images in video, but I'm operating in the time domain. So I wanted to see what the difference was going to be there. With some of the key questions being, if Gangly's using upsampling and one-dimensional convolution, which is basically grow, then shrink a bit, grow, then shrink a bit, I wanted to see what if I did transpose convolution, which is generally a no-no in the image and video domain. But since I'm operating in the 1D space, I wanted to see if there's any applicability there. Now we'll look at the results and the performance. So this is the using the Gangly library. These are outputs from left to right. You're traversing across epochs where you're starting at 1 and we're ending up at 500. And the rows are just different starting points, essentially. So I want to be able to see a couple different samples across all the epochs of what's going to happen. And you can see that it is learning across the epochs. You do catch some artifacts there. And keeping in mind that this is using upsampling and 1D convolution to reduce artifacts. So knowing that the artifacts exist there, I thought that was pretty interesting to the general research problem that I was chasing after. And this is using mine here. So switching over to what I generally am not supposed to use in the 2D world, but I thought it'd be okay in the 1D world. And it looks at a very preliminary level that it did work okay. There's not a lot of artifacts there, but keep in mind that this is a sample of 3 out of like hundreds and hundreds of samples that are available. So the artifacts could be hiding in other images. And here's using the sine waves, and you can see the performance kind of tank a bit. It doesn't look as great as the training data. It doesn't look as clean as the Gaussian pulse had interacted, but it did pick up a pattern, which is generally helpful. And then we'll look at the performance. So we're looking at the error of the discriminator and the generator at the top, and on the bottom of the penalty terms that I was discussing before. It's not worth getting into the details right now for the sake of time. So you can see that the discriminator was having significant trouble in the training process using the Gangly library on Gaussian pulses, and the gradient penalty as well. There's too much volatility. There's not as much smooth as we would like to see. Moving on to mine. We did see that the model converges. We do see less volatility, smoother curves, which are generally better. And this makes sense because of the results that we had seen a couple of minutes ago. Less artifacts and less noise components were in this output. And then finally, for the sine waves, this makes sense in comparison to my Gaussian pulses, where the performance wasn't as great. You could see visually that the outputs didn't look spot on. And this is more or less a mathematical reflection of that. The discriminator and the generator, they are not as converged as you would like them to be. They're not sitting on top of each other. Gradient penalty looks okay, but there's something going on with the consistency term, which was probably leading to the problematic outputs that we had seen. Now, considerations for future work, there's plenty of them, and you could probably really drag this out for as long as you want. But I would start with a more robust analysis of outputs to understand, okay, what do these populations look like generated compared to true? Then I would want to really just dig into some of the smaller components, tinkering more, maybe some change the architecture, maybe more training data, stuff like that, things that would take a considerable amount of work. And with that, thank you.
Any questions?
Yeah.
So these GANs, like, are they similar to how, let's say, if I use something like Midjourney, which is a stable diffusion to take text and then generate an image, is it similar to that, or is it something completely different?
I haven't looked into Midjourney myself, so I don't know about the text moving to video component, but I would imagine, I would guess that maybe there's some translation from text to some kind of vector, and then that vector is getting generated out. Where I went from that 100 up to that bigger thing, that bigger output. I would assume that without looking into any of those details previously, that something like that is going on in the back end to hit that generative aspect of AI.
So I don't really know much about physics informed neural nets, but do you know if there are physics informed GANs?
That I don't know. Generally, I would question the need of the physics aspect, because you can be trying to repeat a certain sequence. So for this example, I'm trying to project a vector. I'm going from 100, I'm trying to expand that vector to make it look like something in the training data. I don't think you would need to know the rules of physics to expand to that, if that makes sense. So, and then you went.
So you spoke about glitches. So what exactly were you doing to counteract those glitches?
So to counteract the glitches, the idea was in the 2D space to go from upsample 1D convolution to do that kind of combination, and that should reduce that. But in the 1D space, I questioned that that idea at the outset. So I thought, what if I use the traditional transpose convolution? Is it going to be worse? And it ended up not being worse. In some cases, it ended up being potentially better before we have like a more in-depth analysis of the result.
So like basically when you tested your model, like did you try attacking it with like more glitches? Or like did you just try attacking your model itself?
Attacking my model?
Like as in there's like a concept called adversarial attacks. I think you spoke about it. You mentioned it in your
Adversarial networks?
Not exactly sure, but
yeah,
apparently like to attack your model with glitches.
No, so the glitches are the representation of the training data. That's just something that exists, and I'm trying to model the glitches. I'm not inserting glitches in there. The glitches are the training data itself.
Okay.